283 million vehicles drive on the roads of the US every day, producing 3.5 million metric tons of CO2. At 20% of the total CO2 emissions, it's a big part of EPA's battle against global warming, or so you would think. As it turns out, the regulations created by the EPA may be one of the biggest contributors to that 3.5 million metric tons of CO2. How is that? Let's get into it. To understand this story, we need to travel back to a different time, 1973. The world was in turmoil, and the United States faced an unprecedented challenge, the energy crisis. That year, the Organization of Arab Petroleum Exporting Countries, or OPEC, imposed an oil embargo. Fuel supplies plummeted, prices skyrocketed, and long lines at gas stations stretched across the country. Americans were in desperate need of solutions to conserve fuel. In response, Congress passed the Emergency Highway Energy Conservation Act in 1974, introducing a nationwide speed limit of 55 miles per hour. This was backed by the idea that cars of the era were most fuel efficient at slower speeds. At the time, this was true, largely due to the body aerodynamics and engine technologies of the time. The new speed limit seemed like a practical way to cut fuel consumption during a national crisis. This action turned out to be more than a temporary measure. To enforce compliance, states were threatened with losing federal highway funding if they didn't adopt the 55-mile-per-hour limit. The Environmental Protection Agency further cemented this as a design standard for automakers when selecting driving conditions for their highway fuel economy test. The driving speeds for the test have a reasonably tight operating window centered to 55 miles per hour. While the 55-mile-per-hour limit did reduce fuel consumption in the short term, it also created lasting consequences, even as the energy crisis faded and technology improved. The EPA's testing methods remained stuck in the past, forcing automakers to optimize for a speed that no longer reflected how Americans actually drove. So why does this matter today? To understand the full impact of this outdated regulation, we need to dive into the science of car design and how modern vehicles are optimized for highway fuel efficiency. Fuel efficiency is driven largely by how thermally efficient the engine is and the loads an automaker determines a car will experience while driving. In general, these two things are coupled and can't be treated separately. However, we can treat these independently when considering automotive classes since similar cars experience similar loads. Hence, we won't find a 3-cylinder engine in a full-size pickup truck or a 6-liter turbo diesel in an economy car. For this reason, we'll look at just the thermal efficiency of similar-sized cars and not compare across automotive classes. If you're interested in the load portion of the problem, perhaps in another video, we can explore the EPA's CAFE standards and how it unintentionally incentivizes automakers to avoid making a variety of efficient vehicles. Leave a comment if you'd like to see that or other videos. For now, we'll concentrate on the highway fuel economy test. Now to the details. An engine's peak efficiency is governed by its brake-specific fuel consumption. This is a measure of how much power you can get out of an engine per unit of fuel used. Many factors play into making an operating map of brake-specific fuel consumption, such as volumetric efficiency, compression ratio, and friction from rotating assemblies. The lower end of the RPM range of an engine typically has a lower volumetric efficiency. As engine speed increases from idle, an engine's volumetric efficiency typically increases before falling off again at the top end of the operating envelope. Meanwhile, having a higher final drive ratio can improve fuel efficiency, but does so by dropping the engine RPM at a given speed. On one hand, your efficiency might improve if you run the engine faster, and on the other hand, it can get better as the RPM reduces. Like this scenario, there are several cases where competing factors can affect the performance of a car. Grouping all of these things and solving for the best set of factors constitutes what's called a single-point input parameter optimization. Since the EPA fuel efficiency test serves as the input, it shouldn't surprise anyone if a car is most efficient at roughly where they're incentivizing the automakers to design around. As a full disclaimer, in the case of the fuel economy test, it's a better example of a multi-point maximization problem. This is where there's several speeds of interest, and you pick characteristics that will give you the best performance over a group of design points. That being said, That same balance of trade-offs still exists, and what automakers look for is a smaller grouping of characters called invariant parameters. One of these invariants is brake-specific fuel consumption. This is because for a given ratio, the maximum thermal efficiency will always be at a fixed RPM. It's a much easier thing to contend with than the hundreds of parameters that go into BSFC. The important concept to understand is if the BSFC is the power per unit of fuel, then that forces the engine's torque curve to peak when passing through the region of the greatest brake-specific fuel consumption. So, with a fixed drive ratio, if the engine rotates any faster or slower than its peak torque, the engine will be less efficient. As a consequence, for an automaker to develop a car with the greatest fuel efficiency, they must align the engine's peak torque with the required road loads. Meeting these loads in several cases assures you can still do things like climb a hill with a loaded car, avoid nuisance shifting, and accelerate to cruise speed at a reasonable rate. Of those loads, the EPA Highway Fuel Economy Test seems to think cars are more sensitive to drag and rolling load design conditions than other losses. These loads would likely account for about 2 to 3% of the total losses in a car when moving from 55 to 65 miles per hour. On the other hand, engines could have thermal efficiency differences in the neighborhood of 10%. Clearly, there's an opportunity for automakers to improve overall efficiency numbers by shifting the load conditions to a more natural speed. Knowing the design space has been artificially restricted by the EPA over the last half-century means no one should be surprised that automaker peak efficiencies have room for improvement. Nor should people be surprised that peak fuel efficiencies are clustered near 55 miles per hour today. After all, that is the design constraint imposed upon them. Setting the technical aspects aside, there are practical reasons to change the highway fuel efficiency test. The primary reason is Americans drive much faster than 55 on the highway, as evidenced by numerous studies from the government, insurance companies, and the prevalence of speeding tickets. On highways, average speeds often range from 65 to 75 miles per hour. According to the Automobile Association, this could result in 10 to 20% fuel efficiency losses. Yet because of the EPA's outdated tests, cars aren't designed to minimize these losses at the speeds we actually drive. Advancements in technology make this mismatch even more frustrating. Today's cars are far more aerodynamic than the boxy designs of the 1970s. They use advanced materials, turbocharged engines, and hybrid systems, all of which could be optimized for higher cruising speeds. But the regulatory framework forces engineers to leave potential efficiency gains on the table, locking vehicles into sub-optimal designs for modern driving patterns. Thanks for watching. Don't forget to like and subscribe for new engineering content.